We have seen that a stack is the simplest implementation of a linked list. The first in first out queue implementation required special cases to deal with the transition between an empty queue and a one element queue. We will now see what is required when a linked list is used to implement a sorted collection. We will examine each of the three fundamental methods for any collection, beginning with the contains method. This method is passed the element that is to be searched for and returns whether it is found. Although this linked list will be sorted, it is not possible to perform a binary search on a linked list because there's no direct way to find the middle element. So this search is a linear search. Because this method will be called by both the add and remove methods, returning a reference to a node that contains the element if it is found, or the element one passed where it would be if it is not found, will not suffice. Those methods will also need a reference to the previous element, which is why we need both the previous and current references that are initialized here. They are both instance variables of the class. The choice of their names, as well as their use, is very similar to the pair of variables used in the iterative Fibonacci implementation. They create a two-node window across the list. Initially, previous is set to null, and current to point to the first node, which is contained in head. The compound while condition causes the loop to stop if the end of the list has reached, which is true when current becomes null, or when the element that is being searched for is less than what is in the current node. The order of the compound condition is important and relies on short-circuiting to prevent dereferencing a null pointer. In our illustration, current is not null, and 17 is greater than or equal to 10, so the loop continues. Next, the value in the current element is again compared with the element searched for, but this time to see whether they are equal. 17 and 10 are not equal, so this condition is false. Had we been searching for 10, we would have returned true at this point. By assigning previous to current, the two-node window across the list momentarily collapses to one node. But the assignment of current to current next, which is the typical assignment in any linked list traversal, widens the window back to two nodes. Although we have not reached the end of the list, the value we are searching for, 17, is less than the value in the current node, 23. Because the list is sorted, it means that 17 is not in the list, so the loop stops. And false is returned. The fact that we are leaving this method with the instance variable previous pointing to the node that contains 10 will be critical if this method was called for the purpose of inserting the value 17, because it will need a pointer to the previous node to perform the insertion. Whenever we are manipulating singly linked lists, working at the head of the list will always be a special case. So with the remaining two methods, we will consider the two cases separately. We will begin with the add method when a value is being inserted at the head of the list. The signature here is the same as with both array implementations. The value to be inserted is passed in, and whether it succeeds is returned. In our actual implementation, we included a second parameter that specifies whether duplicates are allowed. For simplicity, it is omitted here. In the simplified version, we disallow adding more than one copy of any value. That approach would make this method useful to implement sets. If the contains method finds that the value is already in the list, we return false. In our illustration, we will assume 4 is the value to be inserted, which is clearly not in the list. But recall that the call to contains serves a dual purpose. It not only tells us that the value is not in the list, but it also leaves behind the instance variables previous and current, positioned so that they can be used to perform the insertion. In this case, previous is null and current points to the first node that contains 10. The first step is to dynamically allocate a new node and save its reference in the local variable node. We then place the value passed in our case 4, in the data half of the node that was just allocated. And the next half of the new node is modified so it points to the first node, which is what current points to. Next is the check whether previous is null. This condition is true when the value to be inserted will be the first node of the list. That will happen when the value to be inserted is less than what is currently in the first node or when the list was initially empty. In our example, the former is true. So head is now modified so it points to the newly allocated node. We will see that this if statement is common to both the add and remove methods. So in our actual implementation, that common code was factored out into a private method called splice. Finally, true is returned to indicate the insertion succeeded. We will now examine the other case for the add method, when the node is inserted anywhere except at the head. It is worth contemplating whether inserting at the end would also be a special case. But if you work through an example, you will see that it is not. It begins, as before, with a call to contains. But now both previous and current are pointing to adjacent nodes. A new node is allocated as before. This time we are assuming 37 is the value to be inserted. Connecting the new node to the one pointed to by current is the same as before. What is different now is that previous is not null, so this if condition is false. So the else part is executed instead. It makes the next portion of the previous node point to the newly allocated node. This assignment makes clear why it is important that the contains method leave behind a pointer to the previous node. If it only saved the current node, there would be no way to go back because this list is singly linked. Finally, true is returned to indicate success. We now do a similar analysis with the remove method, beginning with the case where the first node needs to be removed. The signature is the same as with both array implementations. The value to be removed is passed in, and whether it succeeds is returned. The method begins with a call to contains, as did the add method, but now failing to find the element is considered failure. We assume that 4 is the value to be removed, so contains returns with previous containing null and current pointing to the first node, the one that contains 4, which is the node we need to remove. Previous is null, so this condition is true. So the head is now changed to point to current.next, which was the second node. You might wonder about the case when this node was the only node in the list. If that were true, current.next would contain a null, which means this assignment would make head null. That is exactly what we want because what defines an empty list is head being null. The node containing the 4 is now inaccessible and will be deallocated by automatic garbage collection, and true is returned, indicating success. The other case is when the remove method needs to remove any node other than the first. We assume 37 is the value we ask to remove, so when contains returns, previous points to the node containing 23, and current points to the one containing the 37, which means previous is not null, making this condition false. So the else statement is executed, and previous.next is assigned current.next, bypassing the node we wish to remove. Note again why it is important for the contains method to leave behind this pair of adjacent pointers. And as in the previous case, automatic garbage collection does the necessary deallocation, and true is returned, signaling a successful removal. Finally, let's compare the efficiency of the operations in the various implementations. With the unsorted array, we did not prohibit adding duplicates, which is why the add method is constant. If we had, it too would have been linear, because we would have had to first search the array to determine whether the value was already present. The contains operation requires a linear search, making it linear, and so does remove. Using a sorted array has the benefit that it can perform a binary search, which is why the contains operation is logarithmic. But both add and remove involve shifting elements, making them both linear. Finally, a linked list can only be searched linearly, and since all three operations involved a search, they are all linear. There's one other consideration that needs to be part of this comparison. It is whether the data structure is dynamic, which is true of a linked list, but not an array. Of course, using an array list or directly implementing one would be yet another possibility, and like a linked list, it would be dynamic.